So have you ever played 3-player bookhouse chess and on the middle board? Well, basically a very effective strategy is to just throw pieces at random until you get something that works. Like literally just try the first thing that comes into your mind. Sometimes when you're running low on time and pieces and are told to stop singing by certain people, well then you might have to think of something a little bit more fancier. But this is rare. Usually just slamming stuff at random works perfectly fine. And ladies and gentlemen, this quote from Max Schindler just sums up this video so perfectly. My dear people, functional equations. So what are functional equations? Well, functional equations are, surprise, well, equations. However, solving those, we are not looking for a number as a solution. We are looking for a function that is our solution. So, for example, the functional equation f squared of x is equal to x times f of x, with f from R to R, which basically just means that f maps the real numbers to the real numbers. Well, this particular one is solvable using algebraic manipulation. Well, if you wanted to solve it, you just subtract f of x times x from both sides of this equality, factor out f of x, and well, get that it's either 0, so a constant function, or equal to x, and well, voila, you just solved your first functional equation. That was lovely, but the problem is that most of the times it will not be so straightforward to solve an FE. And well, we are unfortunately going to be in need of, well, a little bit more tools and theorems or properties. So well, I think it's a good time to talk about those. Ladies and gentlemen, properties of functions. So first of all, guys, injection. So a function is injective if it maps the sets it's defined on in such a way that no two arguments from its domain share a common value from its codomain. So, well, in kind of simple terms, we get that for every x1 and x2 such that an injective function f has f of x1 equal to f of x2, well then it will imply that x1 is equal to x2. Surjective function maps the sets it's defined on in such a way that every single value from its codomain has assigned at least one argument from its domain. So well, no value from the codomain is left lonely without, well, being assigned any argument from the domain. And you'll see why this is so important to talk about in this video in just a minute. A bijective function is both injective and surjective at the same time. So what it means is that it achieves a so-called one-to-one correspondence between the sets it's defined on. So simplifying it, it means that for every single value in its codomain there is exactly one argument in its domain such that, well, those two are linked together by the function. The nice property of those bijective functions is that every single one of those has a so-called inverse function. And so an inverse function is one that takes the value as an input and, well, spits out the argument as an output. And well, those two actually well, converse to each other. So if a function is bijective, it has an inverse, and if a function is, well, inversible, if it has an inverse, then it is also bijective and thus surjective and injective at the same time. And you'll see why this is so important in, well, the first problem we're gonna be doing. One more property worth keeping in mind during our beautiful journey through the world of functional equations is for sure the parity of functions. So a function can be, well, it can be odd. That's when it's symmetric with respect to the 00 point here, like for example the x cubed. And well, it can also be even when it's symmetric with respect to the y axis, like for example x squared. What are the methods for solving functional equations? And ladies and gentlemen, I'm gonna be honest with you here, there are none. I mean, well, there is one, guessing, but apart from that, there is no other one-size-fits-all method for solving functional equations. There are certain strategies that you can take on when, you can take on trying to solve some kind of a functional equation, but there are no methods. Unfortunately, it all comes down to your creativity and, well, your ability to think strategically, also using those strategies that, well, we're gonna be covering in a few minutes. So the substitution strategy is basically, well, a strategy of plugging in certain values of x into the functional equation to gain, well, some intel on how the function involved in the equation will behave. And so a nice thing here would be to recall what we saw earlier, which was that arrow and staff notation. Yeah, so this, for example, say that we have a functional equation f of 3x is equal to 2 times f of x plus x, with f that's, well, double dot, a, an arrow, b, which means that f maps the set A to set B, so A is its domain, whereas B is its codomain, yeah? And, well, right now, the nice thing is that, well, as long as the thing we are plugging for x is in that domain, is in A, well, we can do whatever the hell we want with that x. Well, this means that if I set A and B to be, for example, the reals, this will mean that the equality f of 3 equals to 2 times f of 1 plus 1 will hold, just as f of 6 equal to 2 times f of 2 plus 2, or even f of 3 times pi plus 2 times f of pi plus pi will hold as well. We can take any x we want as long as it's in the domain, and, well, 3, 1, pi, it's all inside of the domain, which is in this case the real numbers. And so we can also just as well substitute in expressions in terms of the variable x, like x over 2 or x squared, as long as they are in the domain. But what does it mean for those expressions to be inside of the domain? Well, for example, let's take a function f that is only defined on the negative reals. Well, now if we substitute in x squared for x, well, we are kind of, well, out of the domain big time here, because we are changing the sign of all of the numbers we have in the domain, and, well, our domain is only negative, so that's kind of crappy. And just as well, we have to be really careful about the domain also when we substituting in numbers, because, well, now imagine we have a function f that is defined only on the positive reals, and we substitute it in -1. How stupid of us. So now that we know what, when, and why to substitute, I guess it's time to do some problems. Okay guys, so the first example of today's video is we're supposed to find all functions that map the real numbers to the real numbers, satisfying f of x plus y times f of x plus x is equal to f of x times f of y plus f of y plus f of x. Whew. Man, I'm gonna twist my tongue today. As hell. Okay, so we would like to do this one using, well, this strategy of substitution. If we didn't, it wouldn't really make sense for me to put it as the first example just after this section where I explained what substitution even is, so yeah, I guess it's kind of straightforward. Okay, so, well, when we are using the method of substitution to solve functional equations, Well, the first thing that is really nice to do is to try some basic substitutions. So, well, stuff like x equal to 0, y equal to 0, x equal to 1, y equal to 1, maybe one of the variables equal to 1, the other one to 0, something like this. I mean, as long as those numbers that I just listed are in the domain of the function that we're looking for. If the domain was, for example, just only negative numbers, I mean only negative real numbers, then maybe x equal to -1, y equal to -1, something like this, yeah? Okay. So, well, let's try and deal with this. Let's do the first substitution. Let's do it towards, well, finding some nice information about the function and trying well, getting to know how it actually behaves. So let's maybe set, first of all, x equal to 0, just as well as y equal to 0. I think it's gonna be kind of interesting. So this substitution gives us what? F of 0 plus 0 times anything is 0, so 0 plus 0 is 0, with f of 0 from the first term. Plus, well, plus 0, so I'm not even writing this stuff down. F of 0 times f of 0, so well, 0 times anything is 0, we get f of 0 on the right hand side as well. Plus f of 0 plus f of 0, so that's just gonna be f of 0, okay, that's awesome. f of 0. Beautiful. Yeah, so well, those two are actually gonna cancel each other out, and we are left with f of 0. I really want to write it as properly as I as I possibly can. As with my terrible writing, it might be a little bit difficult to read what I'm writing here, especially with so many parenthesized expressions. Okay, so we get that f of 0 is 0. That's nice. That's, well, some kind of a first, like, how do you call it online? First property of the function. And well, what are we really trying to achieve by substituting all of this stuff into the functional equation? We want to get some intel on how the function behaves and how this function actually looks like, how it works in the real world, well, somewhere out there where it lives, yeah? And so I would like to actually make a table here, and I will call this a table of facts. And so in this table of facts, I would like to write all of the true statements as we get about the function that we're looking for from substituting stuff. And so the first one is going to be f of 0 equal to 0. Lovely. Okay, so what is some other basic substitution that we can make inside in a functional equation that is defined on the real numbers? Well, I guess maybe we could try and say that x is equal to 1 and y is also equal to 1. Well, that would be absolutely fine by me. So f of 1 plus 1 times f of 1. Okay, this is gonna look absolutely awful because we're gonna have addition inside of this function. That's stuff. It's not separable. It's, well, nobody really knows what to do with it, honestly. F of 1 times f of 1 is gonna be just f of 1, and I have to pop marker because it's kind of dying, and I'm writing is slowly ceasing to exist, unfortunately. And then we are adding f of 1 plus f of 1, which is, well, nicely enough the same thing we had here on the left hand side, because, well, that's my left hand if you're interested, by the way, which is f of 1 plus f of 1. Awesome. So actually those two are gonna cancel each other out. Okay, and we are left with f of 1 equal nicely to 1. Well, that's interesting, because, well, we get that f of 0 is 0 and f of 1 is equal to 1. So maybe we should be on the lookout for example, something that proves that f of x will be equal to x. I mean, that's just some kind of a hypothesis, and I don't really know if it's true or not, but you know, it's interesting. It's an interesting hypothesis for sure. Okay, so what other substitution can we make that is maybe a little bit less basic, but, well, still kind of basic? Well, you know what? I would love to omit the cases where I'm getting those like sums inside of those functions. Yeah,
because, well, here I got lucky, like real lucky, because those two cancel each other off, but I might not get so lucky the next time I do so. So, well, how to get rid of this, you know, get rid of this sum right here and this, I mean, this being a sum right here and this being a sum right there with just one substitution? Well, y equal to 0 seems to do the work, because here we're gonna get just f of x, and here we're just gonna get f of x. Interesting. So maybe we'll make the third substitution with y equal to 0 to get rid of, I mean, to make those two expressions, well, c is being a sum, stop being something like this. But what about x? How should we treat x in this manner? Well, let's maybe set it equal to 1, because, well, why not? Maybe we'll get something interesting off of it. Okay, so what we're getting is f of just 1, f of 1 on the left hand side, plus x is 1, so 1 is equal to f of 1 times f of 0, so f of 0, but f of 0 is 0 already, so we can write it 0. And then f of 0 plus f of 1, so f of 1, which is 1. Lovely. And so cancelling those two, we are getting f of 1 equal to 0. Okay, interesting. That's some property that I would like to write down right here. You see, the problem is that, well, unfortunately, we can, you know, substitute in numbers this problem for however long we wish to. The problem is that we are not getting any solution just from doing that. We eventually have to start plugging in some variables for those variables, well, to get any kind of, well, solution as an expression of those variables, because, well, we're not getting solutions, any solutions, just substituting in numbers. That doesn't make sense. And so how can we make a substitution here that uses variables as the thing that we substitute in? Well, okay, so I'm thinking maybe we could, for example, try and, you know, get, you know, for example, let's right now leave y. Yeah, so I just say that y will be equal to y in the substitution. Yeah, I'm just gonna make substitution number 4, so y will remain fixed. But what about x right now? I would like to simplify this stuff as much as I humanly can by making a single substitution for x. And, well, it kind of seems that x being equal to 1 might actually be a nice thing, because, well, then here we're gonna get f of 1 plus, well, y times f of 1, but f of 1 is 0, so just gonna be f of 1, well, that's gonna be just 0, yeah? At the same time, here's gonna be 1 equal to, well, whatever, this looks reasonable, so let's try and do it. So x will be equal to 1 this time. And so what we're getting is, well, we already achieved this is gonna be 0 plus x is equal to 1, so 1 equal to f of 1 times f of y. So f of y, maybe I will erase the 0 because, well, who needs it here? F of y, and here we get f of, well, y plus f of 1, which is 0, so just f of y. Awesome, f of y right there. Okay, well, this is an interesting property of this function. 1 is equal to f of y plus f of y for every single y in the domain, for every single real number y. Well, lovely. I'll just put it down right here. F of y plus f of y is equal to 1. Awesome. Okay, so what can we do next? So maybe we can make some substitution, maybe with this time x being fixed. So what about y this time? Oh, whatever. So what about y this time? What can we substitute in for y to make this, you know, functional equation as simple as possible? Well, I guess f of y equal to 0 might be a good thing, because, well, here this will disappear. I mean, this y times f of x will disappear. Here this y will disappear. I'm just gonna get f of x here, f of, unfortunately, x times f of 0, which we don't know what is, but whatever, in this function right here, and plus f of x. So, well, I guess y equal to 0 might be a nice thing. I unfortunately wrote it. Yeah, I'm just too fast for a teacher. Whatever, f of x plus 0 times anything is 0, so just f of x and then plus that x, which is equal to f of x times f of 0. We don't know what it is. I mean, we don't yet know. Not y, but 0. Yeah, and then plus f of y0, f of x. f of x. Beautifully. So how do we figure out what f of 0 is? So guys, we got this nice property right there, or even right there, that we achieved a few minutes earlier. Well, y is equal to f of y plus f of y for every single y in the domain. So why don't we just go on and plug y equal to 0. Y equal to 0 right there. Because, well, we know what f of 0 is. 0, by the way. And we are looking for, guess what? F of 0. Oh, we're getting both of them here. So this is 0, yeah? This is f of 0. And so what we're getting is f of 0 equal to 1. Lovely, because now this stuff right here is gonna be f of x. And so we can cancel those two from both sides of this equation. Too many inequalities I've solved on this channel. I'm just twisting my tongue on it still every single time. So we get that f of x will be actually equal to x. Well, that's nice because, well, I honestly thought it's gonna be that way. I mean, f of 0 equal to 0, f of 1 equal to 1. Maybe, intuition works here. So we get that f of x is equal to x, which is the fifth. Oh, this 5 is awful. The fifth fact we achieved. F of x is equal to x. You know what, guys? Actually, those two are the only things we really need to solve this problem right now. Because, well, you see, I don't have to have this y right there. What I really can do here is just plug, and I will use the same framework. I mean, the framework I just put there. Y I would like to plug equal to x in there. And so what I'm getting by this substitution is 1 is equal to f of x plus f of x. But what is f of x? Well, that's x. Oh, lovely, because now we're getting that 1 is equal to x plus f of x. But now, well, algebraic manipulation, we can move x to the left-hand side of this equation, getting 1 minus x is equal to f of x. And ladies and gentlemen, this right here is the function that we've been looking for the past 13 minutes and 30 seconds. Woo! Yeah. Beautiful. Let's move forward. Okay guys, so for the second example, the function f, which maps the real numbers to the real numbers, satisfies f of x is equal to x squared minus x plus a 1, and this time we're not supposed to find the function itself, we're supposed to find its value at 0. Okay, lovely, so I would like to use substitution here, but we are not gonna be doing the basic substitution, because, well, substitute 0 how much you want, well, you're not getting the result here. Yeah, what I would like to do here is show you guys a nice trick right there. You see, the domain and the codomain of the function are the same. Yeah, so we can kind of omit the image right there, and what we like to do is make a substitution such that x will be equal to function evaluated at x. What is gonna give us? Well, we're gonna get that f of x becomes f of x. So f of x will be equal to, well, x squared becomes f squared of x, and then minus f of x, and then plus a 1. Awesome. We know f of x was x squared minus x plus 1. Okay. So that's actually gonna be f of x squared minus x plus 1 equal to f squared of x minus f of x and plus a beautiful 1 right there. Awesome. So, well, we can actually go on and, plug, for example, 0 right over here. Yeah, so we're gonna get f of no, let's make another substitution. So x equal to 0, or x equal to 0, 2 equal to 0, whatever. F equal to, well, 0 minus 0 is 0, so we're just gonna make it f of 1 equal to f squared of 0 minus f of 0 and plus 1. And you know, we'll actually get a pretty nice quadratic equation in terms of f of 0 right there. The problem is that we have no idea what f of 1 is. But there is absolutely no problem in that, because we can figure it out from this line right there. Because now if we take this line and substitute in, let's say it's gonna be our first substitution right there, x equal to 1. What we're gonna get is here, well, doesn't change, 1 minus 1 plus 1 is just 1. We're gonna get f of 1 on the left hand side, as always, and then we're gonna get f squared of 1 this time, f squared of 1 minus f of 1, yeah, and then plus a 1. Well, that's actually pretty nice, because this, after getting this thing right there onto the right hand side of this equation, and then, well, kind of taking all of it and factoring it out, making it square of a linear factor, we're just gonna get f of 1 minus a 1 squared equal to 0, which means that f of 1 has to be equal to 1, which is absolutely perfect, because we can now take this thing right there and plug it here to this equation. And so we actually get that f squared minus f squared of 0 minus f of 0 plus 1 is equal to 1. Perfect, because now those two will cancel each other out when we're gonna get, well, we're gonna get f squared, no, actually, I'm just gonna factor it out, f of 0 multiplied by f of 0 and then minus 1 will be equal to 0. And so, with two options, yeah, either f of 0 is equal to 0 or f of 0 is equal to 1. Unfortunately, we have to choose one of them, because, well, yeah, a function cannot have two values for a single argument, unfortunately. So which one do we choose and how do we choose? Well, this is a pretty nice thing right there, because, well, we know, actually, from this thing right there, from the original equation, that if we plug 0 in here, we're gonna get f of 0, maybe I will call this substitution number for whatever, right here. So I'm gonna get f of 0, f of 0 equal to 1. Lovely. So the problem is that if f of 0 was equal to 0, then f of 0 would be equal to f of 0, but f of 0 is equal to 0, so it would be equal to 0, but it would be also equal to 1. Like, whoa. Well, this doesn't make sense for sure. Absolutely. And so we know that, well, yeah, no, this does make sense, this is true. And so we know that for sure f of 0 will not be equal to 0, and so what we're left with is, well, f of 0 equal happily to 1, and ladies and gentlemen, this is our answer right there.
So creating a system of equations is a method that we use to solve functional equations with those variables that just fly around freely, making a mess there.
Okay guys, so as an example, if I gave you this equation to solve, this functional equation to solve, f of x that is squared is equal to x multiplied by f of x. Well, this one, if I say that, well, let's say f is from R to R, yeah, well, this we actually worked out at the very beginning of this video. Here we can just go on and move this stuff to the left side of this equation to inequality, what the hell, and then just factor out f of x out of there, and get that it's either equal to 0 or x. But the problem is, well, what if I, on the other hand, so this is the other hand right there, gave you an equation, yeah, the functional equation, f of x plus double f of 1 minus x, let's say, is equal to x. Well, let's say that f is still from R to R. How would you expect to do this one using algebraic methods? Well, it's absolutely impossible because of this f of 1 minus x factor right there. It's impossible to get around this stuff. And well, yeah, you know, it actually is possible to get around this stuff. You see, a beautiful thing is that if I make a substitution, let's say my first substitution of this problem, which is x equal to 1 minus x, well then 1 minus x, which is right here, by this substitution 1 will become 1 minus x, which is, well, x, which is absolutely perfect, because now, using this substitution right here, what I'm gonna get is, well, f of x is gonna become f of 1 minus x, whereas 2 times f of 1 minus x is just gonna become 2 times f of x, and x is just 1 minus x. And so, well, I have actually right now a system of 2 equations with, well, 2 variables that I can just solve for, which is absolutely crazy. So now I can just get that, well, from this, for example, I can get that f of 1 minus x, which is what I really want to separate here, is 1 minus x minus 2 times f of x. And so I can just now take this stuff, plug it into this equation, and by doing so, I know out of arrows, I'm gonna get f of x, and I get f of x, yeah, and then plus 2 times all this stuff is just plus 2 times 1 minus 2 times x, and then minus 4 times f of x, and that's supposed to be equal to x. And so, after pumping my marker a little bit, what I'm gonna get is negative 3 multiplied by that f of x I'm looking for, equal to, well, 3 times x minus a 2. And so now I can work this out algebraically. I'm just gonna get f of x is equal to multiplying by negative 1, 2 minus 3x, everything divided by 3. And, well, I think it's really a neat trick right there. Okay guys, so this would be for sure a nice moment to try and do the first problem of today's video, the first proper problem, because, well, the previous ones were just examples. And so we're supposed to find all functions f from R to R, so the ones that map the real numbers, so the real numbers, such that f of f squared of x plus f of y is equal to x times f of x plus a y for all x's and all y's that are in the real numbers. That's actually a problem from, oh man, Kyrgyzstan? No idea how to pronounce it. I'm sorry, Kyrgyzstani people, for not being able to pronounce your country's name. Anyway, 2012 Mathematical Olympiad Lottery. So how do we get about this problem right there in front of us, guys? Well, first of all, it would for sure be nice to maybe try and check whether some basic functions will satisfy this functional equation, to, you know, kind of grasp, well, how this function will, how this equation will behave, and maybe, you know, get to know what we're supposed to expect from the final solution. So, well, the constant function, the most the simplest one, well, it does not work here. I mean, f of x equal to 0 doesn't work here because, well, if f of x was equal to 0, then this entire left-hand side would become a 0, but on the right-hand side, well, just this poor little y will remain, so, and that for sure does not work. F of x equal to x does work here, because if f of x was equal to x, then the left-hand side would be equal to x squared plus a y, whilst the right-hand side would be equal to x times x plus a y. Well, those two, that is the last time I checked, they were equal to each other, so it's lovely. What about negative x then? Well, negative x will also work, because if f of x was equal to negative x, then this entire left-hand side will be equal to a negative x squared plus a y, whereas here, the right-hand side will be also equal to the negative x squared plus a y. Beautifully. So we know we're supposed to expect some kind of a linear solution in the, well, very end of this problem. And now let's move on to the proper solving. So, well, first of all, it would be nice to maybe try and do some substitution to, you know, maybe simplify stuff a bit, and simplify stuff a bit. Maybe try and get, you know, get to know this equation a little bit, how it behaves, how it works. Maybe we'll get some interesting properties of this function that is involved in this functional equation. But what substitution, some basic substitution will actually, well, simplify will actually simplify this functional equation the most? Well, I think that x equal to 0 just as well as y equal to 0 at the same time, this substitution will for sure be a nice one, because then the entire right hand side would disappear, it would become a 0. Well, whereas the left hand side, it wouldn't disappear, so well, I think it's nice. You know what, let's try and do it. So for the first substitution, we will give x equal to 0 and y equal to 0, getting f of f squared of 0 plus f of 0 equal to 0, and that's actually pretty nice property right there, though I didn't draw it perfectly in a straight line, whatever. It's a nice property right there, because now we know for what argument our function f actually spits out a 0. Oh, that for sure will be useful in the future. Okay, this line is not straight. Lovely. So I would like to create one more time our lovely table of facts for the function, and so the first fact will be that, well, f of, let's call it maybe u, f of u will be equal to 0 for u equal to f squared of 0 plus f of 0. I just decided to, like, call this expression u because, well, it's just easier to say u than f squared of 0 plus f of 0, and I would probably, well, twist my tongue on it. Which I don't want to do, honestly. Yeah. So, well, maybe we could use this fact right now. Maybe we could use the fact that there exists a value such that f of that value is equal to 0, and maybe try and simplify this functional equation in some other way. You know what, let's try and do it. So, I'm thinking, well, if we set, for example, x equal to u, well then this x times of x here will disappear, and also this f squared of x inside of this function on the left hand side will also disappear. Well, that's nice. That's for sure a nice simplification, yeah? So let's try and do it. So I would like to set x equal to u, but what about y? Well, I don't really want to do anything with y. Well, let's just say it will remain fixed for this substitution. Okay, so what we're gonna get is, well, f of f squared of x plus f of y will become f of, well, 0 plus f of y, so f of y. F of y here, that's gonna be equal to, that's gonna be 0, y. Okay, well, that's interesting, because now we actually got to know that, well, f of y is equal to y, so, well, f is its own inverse. Lovely. That's absolutely a neat property. So f of not 0, f of well, x is equal to x. I can, I can just put x here instead of y, because I can just substitute x equal to y at whatever time I wish to. Well, they are both the domain, so it doesn't really matter which one I put here. Lovely. Whew. So after establishing this fact, well, maybe we could use it to try and make another substitution for the functional equation. Yeah, maybe we would get some interesting intel about the function from doing that. So I would like to make a third substitution, in which I would like to substitute one of the variables with, well, the function evaluated at that variable. I mean, I can do it, the domain and the codomain are the same, so there's no problem in doing that, but which variable do I actually want to set equal to, well, the value of the function evaluated at that variable? Well, I think it would be better to set x equal to f of x. And why is that so? Well, that would be kind of interesting, because this right hand side, after substituting in x equal to f of x, it would not change. I mean, provided that we let y remain fixed. So this x would become f of x, and this f of x would become an x. Awesome. So maybe, you know what, let's try and do it. I would like to set f of x equal to x and y equal to y. I will not change y here. So what we're getting is f of, well, f squared of x will just become x squared, whereas f of y will remain fixed, and, well, nothing changes on the right hand side. And you know what? Oh, that's actually a pretty nice fact right there, because, well, right now, oh no, this parenthesis is awful. That's better. So it's absolutely perfect fact to know because, well, right now we know that both f of x squared plus f of y and f of f squared of x plus f of y are equal to the same thing, so x times f of x plus of y. So they're actually equal to each other, yeah? Oh, lovely, patch of arrows. Now everything is clearer. Yeah, so what actually we can say about this functional equation right now is that f of x squared plus f of y is equal to f of f squared of x plus f of y. And, well, what do we get from this thing right here? Well, you see, we actually proved that f is its own inverse. Well, if f is its own inverse, then f has to have an inverse in the first place. But if f has an inverse, then f is a bijective function. And if f is a bijective function, then this is also a surjective function. But most importantly, this is an injective function. And so, ladies and gentlemen, what an injective function was? Well, if f is injective, it meant that, well, if f is injective, and we have two arguments such that f of that one argument will be equal to f of that second argument, well, then this would imply that those arguments actually are equal because there are no two arguments that are different such that they will have a common value, yeah? So, well, this actually will mean that x squared plus f of y will be equal to f squared of x plus f of y, and so, f of y and f of 0, and so, after just getting rid of those f of y's on both hand sides, we're gonna get that x squared is equal to f squared of x, giving us, guess what, f of x equal to x, and f of x equal to negative x. That's lovely. Okay guys, but if you really thought that was the end, well, yeah, I have to disappoint you. It wasn't. So, well, we know that f of x is either x or is negative x, but, well, what if f of x is equal to x for some numbers, and for some other numbers is equal to negative x? Well, it may happen. Yeah? We have no idea whether it's true or not. Well, this is so-called pointless trap, so, well, if you just happily ended the problem here and wrote f of x is either equal to x or negative x, well, you wouldn't get, 100% of the points available for the problem. Because, well, this is still a possibility and we have to check it. So, how do we deal with this problem? Well, I would like to suppose that we have two non-zero numbers. It's important that they are not zero. Yeah, so suppose that, well, for example, we have a and b such that f of a will be equal to negative a, let's say. Yeah, and f of b will be equal to b. Yeah, so we see that, well, for some numbers like a, f of x is equal to negative x, and for some numbers like b, f of x is equal to x also. And so we'll plugging into our functional equation, for example, saying that x will be equal to a and y will be equal to b, we're gonna get that f of, well, f squared of x is gonna become f squared of a, so f squared of a plus f of b is supposed to be equal to, well, a times f of a plus b. Awesome. And, well, if you wanted to evaluate this stuff, now we have two options. Yeah, so first of all, we have an option such that, well, the function evaluated at all of this stuff, yeah, is gonna be, well, negative of this stuff right there. Yeah, so the function f for f squared of a plus f of b will be equal to, well, let's for now say just to x. Yes, so we have that f of x is equal to x. lovely. That's the first option, or maybe, yeah, this is not the prettiest I've ever labeled anything, yeah? So this is our first option, and so for that option, when I get that, well, this stuff right there, the left-hand side is gonna be equal to, well, f squared of a, so the square of negative a, which is, well, a squared, awesome, and plus ab will be, well, it's positive, nothing changes here. Here we're gonna get a times negative a, so negative a squared plus ab, well, that would mean that 2 times a squared equal to 0, and so that a would be equal to 0, but it's not true because, well, both a and b, as I've already said, but as I haven't written down, unfortunately, they are both non-zero. Well, they cannot be 0 because it just wouldn't make any sense to say that, well, f of 0 is equal to negative 0, because it's both equal to f of 0. I mean, 0 is both equal to negative 0 and 0 at the same time, so, well, it just wouldn't make any sense. And we also have a second option right there, so for the second option, we're gonna have that f of x will be equal to negative x. Yeah, for this argument right there. And so for that argument, what we're gonna get is, well, still there's gonna be x a squared, and there's gonna be ab. So the left hand side is gonna be negative a squared plus a negative b, so minus ab, is gonna be equal to the right hand side, which is equal to negative a squared and then plus ab, which this time will mean that 2 times b will be equal to 0, and so b will be equal to 0, which is one more time a contradiction. And so both this and that, well, those are contradictions. Whoa, underline even. Yeah, so, well, this means that there is absolutely no way for our function to be equal to x for some numbers and negative x for some other numbers, because, well, yeah, because of this proof right there. Awesome. So, well, we actually get the solutions of, such that f of x is either x or negative x, and this, ladies and gentlemen, is the finish. Is the finito of this problem. Yeah, finally. That was the 8th take, by the way.
So after this beautiful problem, which actually allowed us to, well, use almost all of the stuff we covered earlier, it is absolutely the best time possible to talk about induction in functional equations. Ladies and gentlemen, the Cauchy functional equations by induction.
Okay, so my beautiful people, we're supposed to solve the Cauchy's additive functional equations over the rational numbers. I mean, well, for a function that will map the rational numbers to the real numbers, you will see why rational numbers are as the domain of the problem and not real numbers, I think, at the very end of this problem, actually. And we are supposed to find a function, well, that's actually the, well, Cauchy's additive functional equation, such that f of x plus y is equal to f of x plus f of y, and I think now the name additive makes at least a little bit of sense when you think about it. Okay, so how do we solve this problem? Well, first of all, maybe let's try and, think about some simple functions that will apply here, that will solve this problem, that will solve this functional equation. Well, for sure, the f of x equal to 0 will work, because we don't have any, free variables just flying around and messing everything up right there. So, well, f of x equal to 0 works perfectly fine. Okay. And also, well, the linear functions, or just f of x equal to x, that for sure works too, because, well, here we're gonna just get that f of x equal to, x, whatever. So this is gonna be x plus y equal to x plus y. F of x equal to x works, and actually, well, any f of x equal to some constant times x will work just as well, because here we're gonna get just, that constant times x plus that constant times y is equal to that constant times x and that constant times y. Well, that was a tongue twister, wasn't it? Okay. Okay, guys, so yeah, now that we know what to expect from the final solution, well, maybe we can, try and do some proper solving right now, yeah? So first of all, I would like to do some substituting here. Yeah, substituting, maybe, you know, get some intel about the function, maybe try and see how it behaves, stuff like this, yeah? So the most basic substitution there is, I would like to make first of all, so x equal to 0 and y equal to 0 at the same time, so we are getting that f of 0 is equal to, well, actually double f of 0. Okay, that's interesting. That actually means that, well, either 1 is equal to 2, but I think that's not the case. So it will mean that f of 0 is equal to 0. And I actually would like to bring the table of facts once again, because, well, I just loved it. No idea why, I just love it. Yeah, f of 0 is equal to 0 perfectly. Lovely. Okay, so maybe now something, yeah, still basic stuff, nothing fancy here, but I think it might be interesting. So x may be equal to 1 and also y equal to 1, because why not? So we are getting x of 1 plus 1 is 2, so f of 2 equal to 2 times f of 1, because it's gonna be f of 1, that's also f of 1. I guess 1 plus 1 is, yeah, it's 2, awesome. So f of 1 2 times, okay. Interesting. You see, actually it gets even more interesting, because, well, now if I make, let's say, another basic substitution, so this time maybe I will set x equal to 2 and y equal to 1, yeah. So I'm getting then that f is equal to, f of 3 is equal to, well, f of 2 plus f of 1. Yeah, so f of 2 plus f of 1. But what was f of 2? Well, f of 2 was 2 times f of 1, so, well, this is actually 3 times f of 1. Okay. That's interesting. I mean, this really gets interesting right here. I'm thinking maybe, and you know that I like maybes a lot, maybe f of actually any natural number or any integer will be equal to that integer multiplied by f of 1. Yeah. What do you think about that? I mean, it makes sense for sure. You know what? Let's try and check it out. And how do we check this stuff out? I mean, how do we check if it's true or not, if it's a correct guess? Well, we will use induction. Yeah, my beloved induction. Yes, so for this part, I would like to, well, the base case is actually already achieved here, because, well, we got this stuff, well, it's actually enough of the base case for our beautiful, well, strong induction right there. I love this. I would like to assume for all k that are less than or equal to n, let's say that f of k will be equal to k times f of 1. Perfect. And so now, with this assumption in mind, I would like to prove, I would now like to see what actually f of n plus 1 will be. Well, by literally the problem itself, it will be f of n plus f of 1. But f of n, well, by the assumption, is gonna be equal to n times f of 1. And so, actually, what we're getting here is that f of n will be equal to n plus 1 times f of 1 after factoring f of 1 out. And so this is actually a proof of this maybe right there. Yeah. So actually, well, this maybe will now kind of change into for sure. I would like to actually put this into our table of facts right there. So f of n is equal to n times f of 1. Perfect. You know what? I'm thinking maybe there are some more, properties of this function that will look kind of similar. Yeah. So, let's try and do it. Let's try and find a little bit more of those. But first of all, let me clean up the board because, well, yeah, I'm running out of space here. I love those like really little papers. It's even better than this like professional, full-on. How to say it in English? Whatever. This eraser, whatever. So, well, actually right now I would like to make one more substitution because, well, if I set, for example, x equal to x, so it will remain fixed, and y will be also equal to x. Yeah? So I will just swap x for y. No, not swap. I will just set y is equal to x. Yeah. So I'm getting then is, well, here I'm gonna get 2 times x, and then I'm gonna get, well, 2 times f of x. Okay. You see what I'm getting at, guys, yeah? It's gonna be exactly the same thing once again, yeah? And so, well, now if I make another substitution, so for example, x I will let remain the same, and I will see that y will be equal to double x, and then for absolutely sure, I will get that f of 3x is, well, f of 2 times x plus f of x will just equal to f3 times f of x. And so, well, it would be really nice to maybe try and check whether, check our beautiful new maybe. So our beautiful new maybe is that if we have some kind of a number that is an integer and we multiply it by x and we evaluate our function at that product, it's going to be equal to n times the value of the function at the x itself. Yeah? So, well, we got this beautiful wavy box around our maybe, and now, well, let's try and prove it. So I would like to assume, after, well, noticing that the base case is already done right there, I would like to assume that there exists some kind of a k, no, I would just say that for all k's that are less than or equal to n, f of k times x will be equal to k times f of x, yeah? And so right now I'm getting that, well, if I say that I have f of n plus 1 times x, well, that's actually equal to f of n times x plus nx, which by the problem statement itself is f of n times x plus f of x. And, well, yeah, this stuff right there by the inductive assumption is equal to n times f of x, and so then factoring f of x out will just give us the desired equality. So f of x multiplied by n plus 1 is equal to f of n plus 1 times x. That's absolutely perfect, because now we got, well, those two really, really neat properties right there. And, well, this is actually enough to solve our problem right now. Because, well, you see, we are dealing only with rational numbers. And so numbers that are of the form some kind of an a divided by some kind of a q, some kind of a b, let's say, yeah? And so I can just, well, not even assume, because it's, well, true, as every single x I'm dealing with right there in this problem is irrational, and I just say that x will be equal to some kind of an a divided by some kind of a b. Well, a and b are integers that are co-prime, so, well, yeah, x is rational, otherwise. And so, well, this actually will mean that b times x will be equal to a. But, well, if b times x is equal to a, well, then this means that f of b times x will be equal to f of a. And guess what? We can now use both of the, well, nice properties, the number 2 and 3 that we achieved earlier. So, by 2 and 3, we get that, by 2 degrees and 3 degrees, we get that this stuff right there is gonna be b times f of x, b times f of x, and this stuff right here, so f of a, will actually be equal to, well, as a is an integer, f of 1 multiplied by a. And right now, guys, I can just go on and divide both sides of this equation by b, getting that f of x is equal to a over b times f of 1. But what was a over b, guys? Well, that was the x, yeah? So f of x will be equal to x times f of 1. But f of 1 is just some kind of a constant, so I will just say c, because, well, we have no idea what it is. And this is some unknown constant, and so f of x will ultimately be equal to some kind of a c times nx. And this, ladies and gentlemen, is the solution to the Cauchy's additive functional equation. Okay guys, so I think it's a perfect time to try and work out the solution to the Cauchy's exponential functional equation. So f of x plus y is equal to f of x times f of y, and well, at the function f we're looking for maps the rational numbers, the real numbers. Lovely, perfectly awesome. So first of all, let's maybe think about some basic functions, some of the most basic functions that might actually be the one to satisfy this functional equation. Well, for sure the zero function will work here. I mean, the f of x equal to 0 is gonna get 0 is equal to 0 squared, or both hand sides of this equality, which for sure will be true. Well, the linear function does not work here, but one of, maybe it's not as basic as a linear function, but it's still kind of a simple function. So f of x being an exponential function, so some kind of a constant, let's say c, raised to the power of x. Well, then f of x plus y would be equal to that constant raised to the power of x plus y, which for sure would be equal to c to the power of x multiplied by c to the power of y. And well, yeah, so well, we can actually go about this problem kind of being ready for getting an exponential function as a solution at the very end, and well, you might have actually already thought of that just, you know, looking at the very name of this problem, but whatever. So right now let's do some proper problem solving right there. So what is the first thing I would like to do right here? Well, I would like to, well, make some basic substituting. Yeah, so for example, let's try and do one of the most basic substitution for the starters. So I would like to set x equal to 1 and y also equal to 1. So what it's gonna give me is f of 1 plus 1, which is 2, f of 2 being equal to f of 1 multiplied by f of 1, which is f squared of 1, which is perfect. Okay, well, that's for sure a nice thing. So the second substitution I would like to make here, well, you know what, I'm thinking, with this f of 2 equal to f squared of 1, well, maybe we will get a similar pattern to the one we saw earlier, I mean in the previous problem, yeah? So maybe the integer we put here will be linked to, well, something on the right hand side, maybe the exponent right there. Well, let's see. So I would like to set x equal to 2 this time towards, well, seeing some kind of a pattern, and I would like y to remain just 1 as in the previous substitution we just made. Okay, so what we're gonna get by that is f of 3 being equal to f of 2 multiplied by f of 1, but f of 2 is equal to f of 1 squared, I mean f squared of 1, and so this entire thing is just gonna be equal to f cubed of 1. And well, I'm actually, yeah, I am actually beginning to see a pattern here. So maybe I will just write this beautiful maybe in a wavy box that I will add in just a second. Maybe my thesis right there. So maybe f of some integer, let's say, will be equal to f of 1 risen to the power of that integer itself. Well, there is only one way to check it. I mean, there are two ways to check it. The first one is to just go on and plug infinite limit numbers, and the second one is to use induction. I only seem to prefer the latter. Okay, so I would like to try and prove this one by induction. So first of all, well, yeah, the base case is already done. We've got, well, actually pretty nice base case of 2 cases right there. So I'd like to assume that for all k's that are less than or equal to some kind of an n, we get that f of k, and well, those k's are integers, is equal to f to the power of k of 1. Perfect. And so, well, right now what I would like to do is work out what f of n plus 1 would be, and well, just by the problem statement it will be f of n multiplied by f of 1, but f of n is well, by our assumption, f to the power of n of 1, and so what we're getting is f to the power of n plus 1 of 1, which actually proves our maybe claim right over there. So, well, you know what, let me just bring on the facts table, because I just honestly love it. So we got that the function evaluated as some kind of an integer is equal to this function evaluated at 1 reason to the power of that integer itself. Perfect. So you know what, I'm just gonna make a little bit more space here on the board. Yeah, this freshly opened marker for sure gets erased far more easier for some reason, no idea why. Okay, so now see, if we got this kind of property, which is kind of very similar to the one we got in the previous problem, well, maybe it would be a nice idea now to try and substitute, for example, some multiples of x for y to maybe get some similar property to the one we got here, but in terms of x's and not this one right there. Let's try. So for the first substitution, I would like to set both x and y equal to x. I mean, I'm not setting x to be equal to x because it was just be stupid. So I'm just setting y equal to x, whatever. So what I'm getting is f of 2 times x being equal to, well, f of x times f of x, which is, well, f of 2 to the power of x, f squared of x, yeah, f squared of x, perfectly. And so, well, I think we all know what is eventually coming. We're eventually coming to. So I'll just like to set y equal to 2 times x right now, just for the sake of practice of some basic arithmetic, to get that f of 3 times x is just gonna be equal to f of 2 times x multiplied by f of x, but f of times x is f squared of x, and so this is gonna be eventually equal to f to the power of cube, f to the power 3 of x. And so, well, I would like to right now make another maybe here. So maybe the function evaluated at some integer n multiplied by x will be equal to f to the power of that integer of x, and yeah, the wavy box is absolutely required right there. So I would like to prove it. The base case is already achieved right there. We've got actually 2 cases going to the base case, just as in the previous proof we did like a minute ago or something. So right now I would like to assume that for all k's that are less than or equal to n, we've got that f of k multiplied by x will be equal to f to the power of k of x. And so now I just have to work out what f of, well, n plus 1 times x is just n times x plus x, and what it is. So, well, this is gonna be f of n times x, f of n times x multiplied by f of x, but f of n times x is just f to the power of n of x, and so this is eventually gonna just be equal to f to the power of n plus 1 of x, which absolutely proves our assertion, which proves our maybe right there, and so the maybe becomes a beautiful for sure. Awesome. And so we are getting the second property going into the table of facts right there. So f of n times x is equal to f to the power of n of x, which is perfect because, well, those 2 facts actually solve our problem quite ruthlessly right now. It's perfect. So now we can just go on, combine those 2 and do pretty much the same trick as we did earlier. So I would like to one more time say that x is equal to a over b, where well a and b are integers, and so integers were denoted as a capital Z, yeah? And so, also they are coprime, but whatever, it doesn't really matter. So x is of the form a over b, so x is rational. Well, what it means is that b multiplied by x is equal to a, and what it means, on the other hand, is that f evaluated at b times x will be equal to f evaluated at a. That's because for a single value function cannot have more than one argument, and for one argument it cannot have more than one value, and so this will mean, well, this by the property number 2 will be actually equal to f to the power of b of x, because b is an integer, And well, right hand side is gonna be by the property number 1. It will look something like this, so f to the power of a of 1. And now what I can do is I can just take the root of the degree b of both sides of this equation, getting f of x being equal to f to the power of a over b of 1. But what was f over b? What was a over b? Well, it was just x, and so f of x is equal to f to the power of x plus 1. Well, f of 1 is just some kind of a constant, and so what we are actually getting is some constant to the power of x, which is the exponential function, as the solution. And so, well, yeah, the name is adequate, absolutely. It's 100% adequate in this case. Awesome. And so far what I get. Okay, my beautiful people, so now reducing given functional equations to the known ones. We're supposed to solve the Cauchy logarithmic functional equation, so f of x times y is equal to f of x plus f of y, with f not working from the rational numbers to the real numbers. This time is working from real numbers to real numbers themselves. Perfect. So, first of all, let's maybe check and try and guess the most simple, the most basic function there is that maybe will satisfy this functional equation. So, well, for sure the f of x equal to 0 will work, because, well, both sides of this equation will just be 0 then. Well, the linear function does not work, the exponential function does not work, but if you just look at the name of the problem, yeah, the Cauchy logarithmic functional equation, yeah, there might be something into it, yeah. And actually, if you take yourself a function, f of x equal to log, let's say, base a of x, some kind of a, yeah, then, well, logarithm base a of x times y for any x and any y in the domain of the logarithm will be equal to the sum of the logarithm base a of a and the logarithm base a of y. And so, well, this for sure does satisfy this functional equation and is perfect. A perfect guess, for sure. Lovely. And now let's move on to the section of proper problem solving right there. So, after making this f look more like an f and less like a 7, we can, well, yeah, we can start here, but I'm not going to be substituting in numbers this time, because, well, it is not going to get us anything, honestly. Even, well, substituting in things like variables or expressions in terms of variables, it is not getting us anywhere near the solution. What I'd like to show you guys in this example is kind of like a neat trick, which will actually give us pretty nice solution. Yeah, so sometimes we have functional equations that are so-called reducible, quote-unquote reducible, to some other simpler functional equations that, well, are either simpler to solve or are the ones that we know the solutions to. And so, well, I would absolutely love to kind of reduce this functional equation to the Cauchy's additive functional equation, yes? So f of x plus y is equal to f of x plus f of y, yeah? I mean, I think this functional equation has the potential to do that, and that's because, well, we have this f of x plus f of y on the right hand side right there, so maybe there is some kind of a substitution that will get me to where I want to be. And actually, you know what, guys, there is. Well, if I now make a substitution such that I will say that x is equal to some kind of an a to the power of x, and y will be some kind of an a also to the power of y, well, then my entire functional equation will look like f of a to the power of x times a to the power of y, so a to the power of x plus y in general is equal to f of a to the x plus f of a to the y. And, well, it doesn't really give me anything yet, but if I now make another substitution, but this time a little bit more fancier. So I would like now to create myself a new function right here, and I would like to call this function g, yeah? And I would like to say that g of x will be equal to f evaluated at a to the power of that x. You see, actually, with this substitution, this functional equation I got right there will change into g of x plus y, yeah, because well, g of x is f of a to the x, and so g of x plus y will be f of a to the power of x plus y will be equal to, well, g of x plus g of y. Which is perfect, isn't it? Because, well, this is literally the Cauchy functional equation, the same thing here as we had earlier. And so, well, we can right now just recall what was the solution, two examples before, or I mean, two problems before this one. I'm gonna just say that, well, this means that g of x will be equal to some kind of a constant multiplied by x, yeah? And so, well, what this means is that f of x, f of a to the power of x will be actually equal to some kind of a constant multiplied by x. And so right now, if we just go on and once again just, for example, now I would like to substitute x equal to logarithm base the same a as here of x, because, well, I can do it. There's gonna be substitution number 3. Well, that's gonna give me that f of x is equal to c, which is some constant, times the logarithm base a of x. And ladies and gentlemen, this is exactly the solution we so much desired. Okay guys, so the fourth and the last Cauchy functional equation right there in front of us. So we're supposed to solve the Cauchy's multiplicative. This time the name of the problem does not imply the solution. It's a nice case right there. So we're supposed to solve the Cauchy's multiplicative functional equation such that f of x times y is equal to f of x times f of y, with f once again mapping the real numbers to the real numbers. I have no idea why I'm waving my hands so ruthlessly and so aggressively today. Anyway, so, well, we would like to do the same thing as we did before, in the previous example we just did. And so we would like to reduce this one to a known, some kind of a known functional equation that we solved today. And so, well, actually, I would like to once again make a substitution with some kind of a function, which is a absolutely perfect way to do substitution on stuff. And so I would like to create myself a function. Once again, I will call it g of x. And I would like g of x to be the logarithm base, let's say a, of f of x. And why is it so? Because, well, you see guys, this is actually a perfect tool for reducing my current functional equation into something like this. Because you see, now, if I take logarithm base a of f of x times y, well, nothing really changes here. But if I take the logarithm base a of f of x multiplied by f of y right here, well then yeah, this is actually gonna be equal to what? The logarithm base a of f of x plus the logarithm base a of f of y. And so, well, simplifying all of this in terms of this substitution we just made, well, this is gonna be g of x times y. This is gonna be, well, g of x plus y. G of x right over here plus g of y. And you see, guys, this actually is what? This is the Cauchy logarithmic functional equation. And so what we get from here is that g will actually be equal to some constant multiplied by the logarithm base a of x, which is absolutely perfect, because you see, now we can just go on and make sure that those a's are the same exact a's. So now we just go back the solution, we just make sure that we set g of x equal to logarithm base of the same a as, well, the x right here. Which is like absolutely perfect, because, well, now what we're getting is, well, logarithm base a of f of x is equal to logarithm base a of x. And so, well, ultimately we're gonna get that f of x is gonna be equal to that constant right there, but this x is gonna get higher. It's gonna be x, but this constant is gonna get higher, x to the power of c. And so what we're getting is the function x to the power of some constant. Actually, well, does it work? It does work. F of, well, x times y, yes, so x to the power of c, x times y all to the power of c is equal x to the c times y to the c, so everything works perfectly and just fine. And ladies and gentlemen, this is our solution, and that was the last Cauchy's functional equation. Oh man, that was tiring. Okay, my perfect guys. So once again, well, actually a third example of how to reduce our beautiful equations, our beautiful functional equations to the ones we know. And so, ladies and gentlemen, the Jensen's functional equation of f of x plus f of y is equal to 2 times f of the arithmetic mean of x and y. And well, we actually said that the function we're looking for will map the rational numbers to the rational numbers, and I think it's gonna be just the perfect domain of the problem right there. Okay, so, well, you see, guys, I would love to get rid of this, divided by 2 here in the denominator inside of this function. I would love to, get rid of this plus y or something, and it would be just so perfect if I could, for example, prove that 2 times f of, let's say, x over 2 is equal to f of x. Well, it wouldn't be like, absolutely perfect. We have this 2 right there. It will cancel out with the denominator. But, in order to do that, well, we would first of all have to get rid of this f of y here, and also we would have to get rid of this y right there in the numerator inside of that function. And, yeah, we could, for example, substitute in y equal to 0, and then we would get, after saying y is equal to 0, f of x plus that f of 0 is equal to 2 times f of x over 2. The only problem is that we have absolutely no idea what f of 0 is. Yeah? We don't know if it's 0. It might just as well be, for example, 1. Yeah? If f is, for example, the c to the power of x, yeah, then well, f of 0 will be 1. And so I would like you guys to now bear with me for a short while, so I can show you a beautiful concept right there, which is called shifting functions. Well, if we desperately need some function to, well, be equal to 0 as some kind of an argument, yeah, then what we can do is, well, shift it. So I would like to make a first substitution of this problem. I would like to create myself another function, so I will call it g of x. How long have I been recording those videos today? It's been like, oh yeah, 5 hours. Okay. Yeah, so just everything is a mouthful right now. So g of x will be equal to f of x minus f of 0. Yeah, so I kind of shift that f of x by that f of 0 down. And why is it nice? Because, well, now g of 0 will be equal to f of 0 minus f of 0. Well, that's absolutely 0. So we know that g of 0 will be equal to 0. At the same time, well, it still absolutely does satisfy this functional equation, because, well, those f of 0's, additional f of 0's will cancel each other out, yeah? Because here, if I, for example, substituted it into our original problem, we would get f of x minus f of 0 plus f of y minus f of 0 is equal to, well, 2 times f of x plus y all over 2, and then 2 times f of 0 is just negative 2 times f of 0, so those will just cancel each other out. That would be absolutely perfect, yeah? And so, well, lovely, it works. And so, well, you know what? Let's now just rewrite the entire problem in terms of g of x, and so we will get that g of x plus g of eggs, like chicken eggs, what the hell, man? x is gonna be equal to 2 times g evaluated at x plus y all over 2. And so absolutely lovely thing right now, because I can just make another substitution, which is gonna be just y equal to 0, x gonna remain the same. And so after this substitution, what I'm gonna get is g of x, well, g of 0 is gonna disappear, is equal to 2 times, guess what, g of x over 2. And well, this is exactly what I was looking for. I'm not gonna be even creating my beloved table of facts, because well, it's just a single fact that's gonna solve us the entire problem right now. So now, using this fact, we can just, you know, come back here and say that this is actually equal to g of x plus y. And so what we get in is, well, Cauchy's additive functional equation. This is just saying that g of x plus g of y is equal to g of x plus y, and so g is equal to, well, just c, some constant times x, and so, well, this means that f of x will be equal to some constant times x and plus that f of 0, which is some kind of a constant, let's call it d maybe, so it's gonna be some constant c times x plus some constant d. And so the linear function is the only solution to this. Oh, beautiful functional equation right there. Okay guys, so we are supposed to solve for the function f that maps the rational numbers to the rational numbers with x that is less than y that is less than z that is less than t, where x, y, and z form an arithmetic progression. The functional equation f of x plus f of t is equal to f of y plus f of z. And that's a problem from 2015 Japanese Mathematical Olympiad. And it's problem number 4, as far as you know. Yeah, it is problem number 4. Lovely. So, first of all, what does it mean for x, y, and z to form an arithmetic progression? Well, it basically means for them that x will be equal to some kind of number, let's say a, then y, which is greater than x, will be equal to some kind of a, no, the same kind of an a, but plus some kind of a common difference. Then z will be equal to the same a plus double that common difference, and then t will be the greatest one, and it's gonna be equal to a plus triple that common difference right over there, yeah? And so, well, actually I would like to substitute it into the functional equation, just, you know, to simplify things a bit, because, well, now we have like 4 variables, and this is gonna reduce the functional equation just to 2 variables right there. So awesome. What we're gonna get from substituting this stuff is, well, our function, which we're supposed to find, evaluated at a, plus the function evaluated at a plus triple d, is supposed to be equal to the function evaluated at a plus ad plus a function at a plus the function at a plus 2 times d, which is perfect. Okay, so, well, the problem is that it didn't really simplify stuff. I mean, okay, now, yeah, sure, we have only 2 variables instead of 4. It's a nice thing for sure, but it's still a mess, like a tremendous mess here. And so I would like to show you guys one neat trick for, well, dealing with actually situations like this one. And so in the previous example, we shifted the entire function, yeah? So we shifted the entire function by, well, I could say a fancy word here, by a vector of a negative, of a negative f of 0. And here, actually I would like to shift this function, however, not in, you know, pivot. I would like to shift it horizontally, yeah? So I would like to shift each and every one of those arguments. So I would like to actually make another substitution right there. If you don't know what I'm talking about, then whatever. I would like to say that x will be a minus ad, y will be just a, then z will be equal to a plus ad, and then t will be equal to a plus double d. And so you see, I shifted each and every one of those arguments by a negative d to the left. To the left, your left is here, I guess, yeah. I'm mirroring this video, by the way. Okay, so after doing this substitution, what we're gonna get is, well, here f of x will become f of a minus ad, then f of t will become f of a plus double that d. That's gonna be equal to, well, f of y, which is f of a, and plus f of a plus d, f of a plus d, which is perfect. Because, you know, right now, if I were to sum everything up here, if I were to sum those two, equal this up, well, what would I get is, well, a lot of stuff would cancel here. So for sure, those would cancel each other out. Well, those f of a's would cancel each other out, and yeah, that would basically be everything. Yeah. So what we would get is the function evaluated at a minus ad plus the function evaluated at a plus 3 times d is equal to, well, double f of a plus d. And actually, there's actually a neat trick here that one unfortunately has to notice. You see, a minus d plus a plus 3d, so the sum of those two arguments from those two functions right there, all over 2 is equal to a plus d. And so, in other words, we can rewrite this entire functional equation we've got right there as f of some kind of a minus d plus f of a plus 3d is equal to 2 times f of, well, a minus d plus a plus 3d all over 2. And, well, you see, guys, if we, for example, treat this a minus d as some kind of an x, and this, or maybe not x because it's already taken, maybe some kind of an n, and this a plus 3d we will treat as some kind of a k, well, then this thing right here is gonna be just n plus k all over 2. And so, ladies and gentlemen, this is the Jensen's functional equation right there. And, well, what was the solution to the Jensen's functional equation? Well, it was the linear function. So you see, guys, our function right there, the function we are looking for, satisfies the Jensen's functional equation, and so it has to be, f of x, I will now call it that way, has to be a linear function, so a constant times the variable plus a constant. And, ladies and gentlemen, whew, yeah, that's all for this problem. Okay, so guys, welcome to the last part of this video, and I'm probably supposed to make a big shout out because I found this on the internet with the name of David Young next to it. So, well, great shout out to that guy because, well, his problem is absolutely perfect in visualizing the next concept I would like to show you guys, and actually the last concept I would like to show you guys. So we're supposed to solve for the function that maps the real numbers to the real numbers, the functional equation f of x squared plus y is equal to f of x to the power of 27 plus 2 times y plus f of x to the power of 4. Perfect. Okay, so, well, first of all, what are some basic functions that will probably satisfy this one? Well, probably the zero function. Probably f of x equal to 0, I guess. Probably. Well, I don't really think that any other function will satisfy this, honestly, because it's just so awful. But yeah, let's try it. Yeah, so yeah, what can we do here? Well, first of all, it'll be for sure nice to cancel some stuff out, yeah, but how? And you see, I just thought the solution to this problem is so beautiful. I would like to cancel for example those two off here, because, well, here we have this x and some y, here we also have some x and some y, you know, stuff like this, yeah. So here we have just two variables, here also we have two variables. So maybe there is a chance to, you know, make those two equal to each other with some kind of substitution. And we're actually going to make the most idiotic substitution possible, the absolutely most stupid, the most stupid one. So, well, first of all, I would like to figure out what substitution even to make. So I'm going to set those arguments equal to each other. Yeah, I love it. Well, actually, this is a valid trick. It's absolutely legal, absolutely awesome because it works. Yeah. And so what we're getting here is, well, that x squared plus y is equal to x to the 27th power plus 2 times y. And so y is actually equal to x squared minus x to the power of 27. And so this is exactly the substitution I would like to make here. And so I would like to say that x will remain fixed, however y will change it to, or not y, but x squared minus x to the power of 27. And so by this substitution what I'm getting is, well, f of x squared plus x squared minus x to the power of 27, so 2 times x squared minus x to the power of 27, is equal to f of x to the power of 27, x to the power of 27, plus, well, 2 times x squared and minus 2 times x to the power of 27, so, well, those two are equal, and plus f of x to the power of 4, which basically means that f of x to the power of 4 will be equal to 0. And we are not done yet, because, well, the problem is that we are supposed to solve this function over the entire real numbers, and the entire set of real numbers. The problem is that, well, x to the power of 4 is only, unfortunately, only positive. So what we did here is we solved this problem only for the positive real numbers. But, you know, there's absolutely no problem in that, because, well, what we can do now is just, well, say that f of x, or maybe I will just say f of x is equal to 0 for positive x's. Perfect. Now I would like to use this to make the second substitution right here, because, well, if I get rid of those y's, well, then f of then x squared here instead of this f will be positive, and this x to the 4 will also be positive. But, well, this x to the power of 27 is not necessarily positive, and so, well, perfectly. I would like to, well, let x remain fixed, and I would like to set y equal to 0, getting f of x squared on the left hand side equal to f of x to the power of 27 plus, 27 is awful, 27, and then plus f of x to the power of 4, but those two are actually zeros, and so what we're getting is that f of x to the power of 27 is also equal to 0, but, well, x to the power of 27 can actually be also negative. And so what we're getting combining those two facts is that f of x is in general equal to 0. Whew, that's the only solution there is. Whew.
Okay, so that would be all for today. That was tiring, like real tiring, big time. I really hope you enjoyed this video and got some value from it. If you did, well, I'm happy, you're happy. It's a win-win situation for both of us. See you in the next one.